recording on my side. Oh, it just took a delay, it looks like. So, okay, let me introduce real quick so it's on there again.
Yeah,
So, it's my
again,
great
please.
pleasure to introduce Alexander Konovalenko on Iterated. He's going to be talking about iterated completely positive maps and measurement controlled dissipative two-qubit dynamics. So, Alexander.
Yes, thank you. And hello, everyone. Today I will speak about this iterated completely positive maps in measurement control and dissipative two-qubit dynamics. And uh, first of all, the physical setting here is a two-qubit system interacting with environment, so the evolution is not pure unitary. At the same time, we apply some repeated joint measurements in entanglement basis, and this naturally leads to a discrete time dynamics obtained by composing a dissipative step with a measurement induced. Well, so that my talk has two complementary viewpoints. Physically, I want to show how repeated joint measurements can slow the loss of coherence and entanglement. And mathematically, I want to describe the whole construction as an explicit family of iterated completely positive maps acting on trace class operators. So, let's start. The main question here is whether repeated joint measurements can change the effective dissipative dynamics of an open entanglement system. There are two versions of the protocol. The first is some projective version corresponding to the strongest measurements action, and the second is a weak version where the measurement strength is controlled by parameter q between 0 and 1. Yeah, so the main conclusion what come from our works is that even with the measurement when measurements are not fast enough to produce the standard quantum xenofreezing, they can still subsequently preserve entanglement. So the correct picture is not full freezing, but controlled like modification of the dissipative channel. Here you can see some theoretical setup of how it works. Yeah. Next one. Yeah, so now I want to introduce the one-step channel family. The update here the update is written schematically as row at step k plus 1, and it is approximately the measurement map M. Yes, on a controlled step on the this measurement map n, like on this sublittle q, on composite with the exponential with the UNAS exponential is subscript this limit operators L times on delta t acting on rho with the step k. Yeah, so our this exponential script here is a dissipative step generated by a Lindbladian. Yeah, this one little l. Yeah, big M, it's a measurement controlled step on the Bell subspace, and Q with strength 1 is a projective subspace filtering, like this strong version one. Yeah. And the next one is a weak measurements or partial collapse, where we between 0 and 1, and we can tune it. So, we can say that like after some n iterations here, we can obtain the family phi with parameters q and delta t iterated n times. And this is the central mathematical object of our talk, and it depends on measurements on the measurement strength q, the number of steps n, the relaxation rates gamma 1 and gamma 2, and the pure diffusion rates. It's gamma p1, gamma p2, the Planck number n, like kinda temperature parameter, and the qubit frequencies, omega 1, omega 2, and the parameter of the initial superposition p. Yeah. Let's go further. The next point is a state space. We work on a two-qubit Hilbert space. here where our which is isomorphic to like a complex four-dimensional space, and our dynamics act on the space on the trace class operators. Yeah, so the relevant entanglement sector is the Bell subspace. Which is the span between like psi, like with psi plus, у нас psi plus, psi minus, when with such Bell vectors, with such Bell vectors, we have cat like 0, 1, plus or minus cat 1, 0 divided by square root of 2. So, and the typical initial state here is presented like Z. As you can see, like phi from like this phi from P, like equal square, like our square root from this P, and which acting for our next, like this part of cat. Yeah, so, and the main physical idea here is that we may not know the exact protected state, but we know that it belongs to prescribed entanglement subspace. That is why the measurement protocol is naturally formulated at the subspace level. So, let's move on. And the next one is a standard QZR. Before we go into the open system case, let me briefly recall you the standard quantum Zeno effect. For a time-dependent Hamiltonian, the state psi of t usually equals exponential or exponential of this minus I is Hamiltonian times t, and it's acting on a psi 0. And the projector here is the initial state. Onto the initial state is p equals cat cat psi 0, like cat psi 0 bra psi 0. So after the repeated projective measurements, the state here is obtained by alternating the Hamiltonian propagator and the projector P repeated n times, and they're normalized by trace. Yeah. So, the survival probability is the absolute value squared of bra psi of this bra psi 0 exponential, like of this nearly same equation, but with delta t. This in this case, and by cat psi 0. Yeah, so which we could for in short time expansion is looking here like z1 minus delta t square times and the t square times with the variance of with the values of our Hamiltonian in the initial state plus some higher order terms. So in the K point here is that the purely unitar case. In the unitary case, the deviation from one is one is a quadratic in delta t. That is why the what allows the no freezing. But in open system case, linear terms survive, so freezing is lost. And here we come for the next point. It's open system. The free open system, like in the real world here, is here dynamics is generated by Lindblad-Lewis. So here we go our raw like future probability density matrix, which is equals equals input from raw, or with more open case, it's looking here like z like minus I times the commutator of our Hamiltonian and rho plus the sum over all this part which exactly describes this influence. So the Hamiltonian here divides for first qubit and for second qubit alike. And here we have Lindblad operators, which split into groups. First one, it's with linear. First one with linear terms, which describes linear energy exchange with linear exchange with bus, yeah, with thermal bus. And the second one, which describes pure dephasing. Yeah, and for every positive time step, yes, we have such apparatus acting over our system. Yes. So here we have the map exponential of script like this uh, these formulas which explain it, and all these dissipative channels that we later compose with the measurement maps. So uh, let's go further. Now for projective measurements. In the projective protocol, the admissible Bell sector is selected by projector P plus, P minus, where P plus or P minus it's equal, like previously discussed, cat psi and bra psi, like such condition. And here we have some projective updates for after free evolution, looking like that, similar. And we can say here that mathematically the numerator here is defines a linear completely positive map. It's like this part of free evolution, and it is trace non-increasing because only the successful branch is retained. The final normalization make the full state update nonlinear. So when I speak about iterated completely positive maps, I mean the linear maps like before normalization. Yeah, so go next to the next point. And the weak protocol replaces strong measurement by a tunable measurement apparatus. Here we see a Q, which we could set between could be between 0 and 1. And yeah, and the updating state we could get in the like quite a similar way. Yeah. So, and here also, if we make a Q like 1, we return to previous strong projective measurement case. And if we make Q lesser than 1, it will be such a gentler like back option. And we have more space for some experiments. So here it's like make the role of Q more clean. Yes, when Q like equals 1, we recover the strongest return to the Bell subspace, and when Q is smaller, the back actions is weaker, but the dynamics is still biased toward the desired intelligence sector. Right. So next one is the about unifying channel viewpoint. This is now like a main slide from the operator theoretic point of view, because the controlled one-step map is the phi with our parameters q, delta t acting on rho, equal to the normalization map applied to the map m is sub q, yeah, applied to the dissipative step exponential exponential of script of such a subscript like L or and delta t acting on the row. So there are like three layers. Dissipative channel, like first one. The second is a Bell subspace measurement map, and third one is this n times iteration. And the like correct mathematical interpretation is the following. So the free step is a completely positive trace preserving map. The measurement filter is a completely positive trace non-increasing map. And the normalized output is the conditional state on the retained branch. So this is like a precise meaning of the phase iterated completely positive maps in these settings. Yeah, so and now we came again a bit closer to the physics for short asymptotic formulas which we can get is for free evolution the Bell sector of diagonal elements rod of these these matrix elements to rho to 3 is looking like that. And with repeating projective measurements, we could achieve such equation where, as we see, these formulas show us exactly what is being suppressed. The terms, the Hamiltonian terms disappears. The linear energy exchange terms proportional to gamma 1 and gamma 2, as you see, also disappears. So the left one is only the pure dephasing part, which remains. Yeah, and the next point here is to quantify like this effect physically. We use two observables coherence measure here. And the second one is concurrence. Is concurrence. So the interpretation also is quite simple. The first one tracks coherence directly, while concurrence tracks the entanglement resource, irrelevant for quantum, which is very relevant for quantum information, which we actually tried to say. Yeah. And here we have a first part of an even numerical result. Yeah, for small time concurrence. So by these two equations, we could set this as a short time asymptotics, which have a very good correlation with experimental result. Here are maps like in real time, alas how it look like these little steps. Yeah, this blue one. Yeah. So next. For the next result, we could look for some uh, uh, um, mm, for some ways to quantify this protocol. This like these three characteristics, and this tangential effectiveness. It's like angle between those line as on previous slide. Yeah. So the steeper line, the more line like upper, it means our result for saving entanglement is better. Second one is time, is how long we go upper the concurrence of measurement 0.9, and the third one is the coherence as we described before. Also, we could have some asymptotic tangential effectiveness by these presented formulas. Yeah, so let's go for some more vivid results. Yeah, can we see matrix trajectories for this two-qubit system? Yeah, can we see our asymptotics marking this solid line, and our simulation which show like pretty strong result already on these 50 measurements. Yeah, so and data from coherence F4 times part. Yeah, so next one is a density matrix snapshots, like is start one. You see this one, we lose all in the middle. It's when we have not suppressed the coherence, and here when we used our measurements, use our iterated maps, and it's helped us to save these blue blue parts and so on. So we saved entanglement. Yeah, it's kind of good say. For the weak measurement case, it's or even more pronounced. It's for different case. Like it's more weaker measurements here you see. Also, it's how it affects the density matrix here. So, and for effect, we have a weak for weak measurement number. We see yes, really as we weaker with weaker measurements, with weaker applying influence of these our projectors, we have lesser results, and with more some interesting behavior. Yeah, and this literally it influence. So the next point is influence of different physical parameters. Yeah, it's show especially this part as with increasing of temperature we show better results because this is the exact part which our measurements, our maps could suppress. Yeah. This is what dependence were moderated and already like our measurements sufficient, no ultra-fast measurement needed. Protocol helps more with linear coupling over pure defuzzing. Yeah, temperature makes matter even like a bit more better because we could work out with it, and the effects weaken, of course, with when we leave idle Bell subspace here, but we still has some effects. Yeah. So and for the some like summarization, we could say that repeated Bell subspace measurements suppress the Hamiltonian phase of evolution and the like linear energy exchange path, meaning the terms proportional to gamma 1, gamma 2, but they do not remove the pure defuzzing terms gamma p 1 and gamma p2. So the controlled maps are they changed the effective contraction experience experienced by entanglement sensitive or observables. In other words, like phi with such parameters q and delta iterated n times contracts concurrence more slowly than a free evolution does. So the like a main message I want to leave is to leave you with is that measurement is not only like observation here. It acts as a selective, completely positive control mechanism on the admissible entanglement subspace, and in that way, it modifies the effective dissipative channel, which is very used as for physical field and quite interesting for mathematical field. So, yeah, thank you.
All right. So thank you, Alexander. Please, everybody, join me in thanking him. So let's